Well, good morning. Very pleased to have TopCon here today to talk about their corporate-sponsored senior projects. You can see there's a very cool-looking machine here that they're going to explain to you and talk about the context of what they're calling the Sambuca study.
Well, thank you. My name is Donna Kelly, and I'm doing advanced product design and product research at TopCon in the Livermore Engineering Group. And Joseph Parsons, perhaps there are some of you who know him. He is a graduate of Santa Cruz here, and he is working in our group. We're working on a couple of projects together. We're here to talk to you about a proposal that we have for a senior project for you that we're pretty excited about. Slide. Oh. And as we move forward, Joseph and I will wrestle over the microphone through this thing. Okay, so a little bit about TopCon. TopCon is a Japanese-owned company, and they started out in 1932 doing optics, survey optics, and photographic equipment. And they're one of the original innovators in the single-lens reflex area, eventually selling their patents, I think, to Nikon. So if you are a camera buff, these guys were an unknown but important part of your hobby. Do you? Okay, there you go. Okay, 1932 they got started. 1994 they established the group that Joseph and I work in. That's the machine positioning that's located in Livermore. The machine positioning business, as far as TopCon understands it, or the way we express, is for construction machinery. So we position the machinery relative to the work. So if you have noticed that roads have gotten smoother and flatter over the last couple of decades, yeah, right. There's the improvement in technology, and then there's the lack of maintenance. But these, so new roads have gotten smoother. So we put control equipment on bulldozers, motor graders, excavators, so that they can work very accurately to a design model for the site where they're doing the excavation. Okay. Good. Very good. Okay. Now, our focus in Livermore is entry-level applications, so low-cost applications, so small machines, skid loaders. This is a skid loader. This is a wheeled machine. It has a bucket on it. This is called a CTL, or a compact track loader. These are really the same machine. They're the same in everything except for the part that touches the ground. And these kinds of machines are being used more and more in construction environments. Up here? Ooh, whoa. That's, wow. Okay, so these kinds of machines are being used where small bulldozers used to be used. They're also used as general purpose machines for a wide variety of applications that previously had to be done by hand. So one of the interests that we have at TopCon, just like everybody else in the world now, is to make these machines autonomous. So right now, we provide guidance for the machines. They'll work to a design criteria, but the machine is basically driven by a human being. We want to get the human being out of the cab. So in Livermore, we're working on these small machines. And for these small machines, because they're budget constrained, we don't get to put big fancy LiDAR on the machine. We don't get to have a lot of computational resources, and that makes it for a different challenge. So we have some priorities. We have inexpensive sensors, and in general, vision-based sensing has the potential to be less expensive than other types of sensing. We want to look at small data, and we want to do this task-centered localization. Task-centered versus world-centered, right? Okay. So does that make any sense, task-centered? Anybody have a question about what task-centered means? Now you all know, because that's what you do. Okay, so next slide. All right, so this is a kind of an overall description of one of the demonstration applications that we've planned in order to show that we're working on a useful set of skills for the machine to have. So this is like a top-level decomposition of the task of moving a pile of dirt from one place to another. So the first thing is you have to specify the task so the machine knows what even you want it to do. You need to get over to that first stockpile. That means you have to have some navigation capabilities, and you have to understand that stockpile as a target that you are going to address. When you get close to it, you have to decide now exactly how am I going to approach this task, right? So I've driven across the site, but now I have to actually decide where am I going to take my bucket full out of this pile. You have to fill the bucket, harder than some people think. You have to get over to a dump point to get rid of it, and then come back and get another bucket. And so this is the thing. These ones in red are the scope for the project that we're proposing to you, okay? Now, I've been around the world. I've been to Finland to see some graduate work on this same topic, and we watched a skid loader address a pile of gravel and take 1/2 bucket from it, and then come back and take 1/4 of a bucket from it, and then come back and miss the pile entirely. Okay? So this is an opportunity for you to be involved in doing something correctly for the first time.
That'll be new for you.
Yeah. Okay. All right, next slide. Okay. So the specific scope of this project, we want you to do a bucket filling algorithm. And what we think that involves is you'll have a point cloud, or you will generate a point cloud that represents the target pile. We want to do this using a very rudimentary sensor system. So we're going to provide you with a Raspberry Pi-based stereo vision system. And what this does is it'll take 2 video streams and calculate a disparity map from them. And if you think about it, a disparity map is actually equivalent to a point cloud. It's just in polar coordinates instead of in linear orthogonal axes. So you can take that point cloud and use that as a model of, I'm sorry, I just broke the machine, of, of the pile of dirt that you're going to address, okay? You'll need to calculate the optimal approach vector for that pile. So here we have this sort of amorphous lump of dirt. It actually has a shape, right? So you want to think about what's the best way to approach that pile of dirt so that I can get a full bucket. This is especially important when you come back for the second bucket, because if you come back to the exact same place you started in, that bucket's already been taken, right? So you're going to want to find a new optimal direction and location to approach the pile from. You have to get into the pile, so you have to penetrate it. And the important thing about this is to know that you've actually got material in the bucket. Like that example that I mentioned earlier, this machine is blindly driving around, lowering the bucket, driving forward, picking up the bucket, and driving away with nothing in it. So to have the sensual awareness to know that you've got a good load of material in the bucket is very important in this case. Okay? And that's especially, so when you come back again, so you'll see what we've put here in the slide. My first approach, I'm going to pick some place that seems rational to address the pile. The second approach, that bucket full's gone, pile has a different shape, I need to approach it a little bit differently, and so on. I may come to places where I have multiple areas on the pile that meet whatever criteria you have selected for deciding where to take a bucket full from, and then you have to prioritize between them. Okay? All right. Things you, oh, go back one, please. Things you don't have to do. We'll get you to and from the vicinity of the target pile, so you don't have to worry about the overarching navigation issues or identifying the target pile and so on. We'll get you there. You don't have to worry about the destination. We'll take that out of your scope, because what happens is if we put too much of these things on, they all require different competencies, and we want to get you focused on what we think is the most interesting part of this, which is selecting a bucketful out of the pile. This is the thing that nobody else has done yet. Okay? What we'd like you to do is generate the proof of concept code for that part of the application, and we'd like you to come to Livermore and demonstrate it on a real machine. So next slide. We'll talk a little bit about the platforms.
All right. So so this is a really cool opportunity for you guys to
work on something, platforms that you haven't worked on before, or expand your knowledge in actual real world, using of, say, OpenCV or something like that. So obviously we've got a lot of stuff going on this little guy. So this little guy is basically a very small scale model of something we have at the office called the M48. The M48 that you'll see pictures later on is much bigger. It's a remote controlled dozer basically, but a big one. And so this is a little one. And so, yeah, so this is the M48 right there. So as you can see, it is human sized, still not as big as a real big dozer, but you can control it with a remote control. And the idea is that we can tap into the M48's control systems and basically put all this stuff on it, the Raspberry Pis, the cameras, all that. And with a little adjustment in the code and whatnot, we can make him work the exact same way as this guy.
No adjustment in the code.
Oh, sorry.
Interfaces are identical.
Interfaces are identical. Adjustment in the camera placement.
Well, it's
Kind of,
all
maybe.
right there, so all we do is we just
All right.
bring
Yeah.
the ROS node over and run the big machine.
Perfect. All right. So anyways, so this is a chance for you to learn some really cool, new, interesting skills and stuff. Have some real world experience in doing these things. So this is just a short list of what we're using. We're using a lot more, obviously, but you have Raspberry Pis. You're going to be dealing with them. We have two types of cameras on here actually. So we have the stereo cams themselves, and then we have an additional camera that
We use that one for
the disparity map,
site
right?
traversal, so that's probably outside.
Yeah. Oh, okay. All right. But the cool thing is basically you're going to be using so the robot operating system ROS. You're going to be using that. You're going to be using C++ to code in that. Raspberry Pis, among other things. And basically, it's a really cool way to get get your hands in a lot of different fields, a lot of different areas, and expand on that. And basically, by the end of this, you should be, a certified genius in this stuff, in autonomy. I could do this.
You want me to just send it over? Okay. On the platform side, these are components that we actually use in our day-to-day work. So this is real-world environmental stuff. I think a lot of you are probably familiar with some of it.
All right. So, wow, that is loud. Okay. So the task for this guy, it's relevant to small machines, as we already said, and this is kind of what we want. Stepping into your guys' task, this is kind of how to define it. We want phases, well-defined state changes. So this is something that can get you in a lot of trouble if you don't have well-defined state changes. For instance, when you fill a bucket, how do you know to either keep filling the bucket because there's not enough dirt, or to say, look at it and say, that's enough dirt, I'm going to back out. So I can already, foresee one of the problems is you'd start filling the bucket, and maybe your algorithm is you want to get so-and-so to a point, inside the dirt pile. You want to get so close. But you're losing traction, and so you're stuck in this state of you're spinning your wheels and stuff. So you need to go through, think about these types of things and define them, and have states for them and error codes and all that.
All right. So that's why it's such a cool thing to do. All right. So, oops, wrong direction. Okay. We're pretty funny, aren't we? Yeah. Okay. The resources that we're going to provide. This is the HouseCat Mark II. It's the second of the office size equipment that we've designed at Livermore to help us working on these tasks. The idea is that M48, it's big, it'll hurt you. We can't run it in the house. So we've built these little small machines that have the identical interface and the identical functions to it, so that our engineers can come up with an idea for an algorithm, a steering algorithm, sensor set, that sort of thing. They can try it out easily in the office. So we'll be sitting there at work and this thing will come trundling by. So that's kind of cool. We're going to loan you one of these for the duration of the project. So this is not a hardware project. This is an algorithm development. And we'll provide you the working house cat model with the identical interface to that M48 so that you can take the work that you do on this and take it directly over to a real piece of equipment, and we'll take it outside and we'll cut dirt with it. Okay. So you're going to have this thing for the duration of the project. You'll also have the opportunity to come up to Livermore, visit us, and mess around with the M48, understand it, try things out on that to the extent that, that you feel that that's relevant to your progress. At the end of the term, we do want you to take your algorithm and put it on the M48, and we're going to go out and all stand around and watch how good it works. So, okay. TopCon personnel, there's me. Useless. And there's, and Joseph will be the primary contact and interface to you guys, to your program. We have an engineering team. I wanted to get a picture of them, but I couldn't find a picture of the whole group handy when I was putting the slides together in a hurry. We have a group of about 10 or 15 engineers, any number of which might be useful to you at different parts of the development. And so we will support you on the development of this project. Okay? So you'll be able to have the opportunity with engineers actually working in the machine control field. Okay? I think that's it, right? Yes, do you have any questions for us?
Are you interested?
I saw one guy nodding.
Quiet class.
Yes?
Shy.
Okay. Yes? Oh, absolutely. Okay. So, okay, the question is, what's the difference between task-centered and world-centered localization? I don't know if world-centered is a actual phrase, but global coordinates, in the autonomy world, GPS is a big thing, and precision GPS is something that TopCon does very well. So we can tell, if you're outdoors and you have good access to satellites, we can tell where you are to a few millimeters. Okay? So that's a tremendous amount of precision. That's a tremendous amount of control that is available. It's a little bit expensive to do that. But the other thing is, if you are doing, so let's say you are, want to move this pile. Let's find the slide with a picture of the task. Yeah, you want to move this pile. Now, if you're going to use world coordinates, you have to know where that pile is. And if you are using world coordinates to understand the shape of that pile, right, you can do that. But, and that's generally the approach that people take so far, is they say, I know where everything is in the world, so now I can command my robot to drive around in that world, okay? But the robot is essentially blind in that case, right? It knows where it is. It knows where everything else is supposed to be. But if you've ever looked for your classmates for a study session, things are never where they're supposed to be, right? So the idea of task-centered localization is I don't have to know where in the world this pile of dirt is. All I have to know is where I am relative to the pile of dirt. So in our case, all of our mapping or our localization will be done relative to the task. I care about where my implement is and where that pile of dirt is relative to each other. And that's really the only thing I care about. Does that reasonable explanation? And that suggests a different type of sensing and a different type of mapping. So SLAM is very useful for task-centered localization because I don't have to take my point cloud or the map that I'm generating from my simultaneous location and mapping algorithm. I don't have to locate it in world coordinates. It means I can't attach it to somebody else's map because we don't know where we are relative to each other. But for whatever I'm doing right now, I can stay within that local framework. Long answer. Not sure it was a really good answer. Yes? Is there already an algorithm for the most successful way to use the shovel? No. So that's part of the problem. Now, what we can do is we can talk to you about how humans operate the shovel, okay? So if there's a guy in the skid steer, there's some tricks he knows. For example, he can drive into the pile with some momentum, right? And that will help him penetrate because in addition to the force available from his traction, he has his forward momentum. Another thing that they'll do is they'll shake the implement a little bit because that loosens the material around it. So we can talk about those kinds of things. And you know, if it makes sense for you to have a field trip and go out to some kind of a site where they have building materials and they're using skid loaders and stuff to load trucks and things like that, you can go out there. In fact, there's a big building materials place just down here by the river, I think. So you can, that should be something that you consider part of your scope is, how am I going to effectively do this? Sure.
That pile of dirt that you're showing there, how many points in three-dimensional are you going to provide them with?
How many?
In other words, can you see behind the pile so that you actually know the relative volumetric shape of the pile?
So the question is, how good of a point cloud of the pile are we going to provide you? Well, what we're going to provide you with is a very poor quality disparity map from this stereo head. Now, I'm not sure that the algorithm that we're using, it was developed by an intern who worked for us last summer. And it gives a kind of a really rough disparity map. You might want to improve it some. Obviously, the disparity map that you're going to see from the stereo camera is only going to give you the side of the pile facing you, okay? So question for you is that sufficient for you to optimize your vector, or are there cases where you need to know more about the pile? Can you augment that by remembering what the pile looked like before, the history of the shape of the pile that you saw? So part of the cleverness would be to work with incomplete data, okay? Obviously, one risk is, the slide that has the consecutive bytes? Yeah, there we go. Obviously, one risk is if you don't know what the back of the pile looks like, you eat away the whole front of the pile, you get to something thin that you think is still a significant pile, and you just pop through it, right? When you actually wanted to come and run from an edge. Now, is there some logic or intelligence or some judgment that you can apply to say, oh, my pile used to be this tall, now it's this tall, and I've all been working from one side. Does that suggest that I don't have as much depth, right? So, right? So you want to be, you want to think a little bit outside the box on the logic for accomplishing this task.
I have one observation here. I think the very first test for a groove is to make sure you can distinguish between a shovel and a bucket. So this is not a bucket.
Oh yes, let me explain that. We just brought this is one example of one of the implements that we've made for this. Yeah. Yes. This is a general purpose tool for us. So we configure it as a dozer, or we're in the process of building a bucket with an articulation similar to this. And the picture of the house cat that's in here shows this. Down. One more. One more. There we go. So this is in construction right now, is this, this bucket that emulates the bucket on a skid steer. So, as we move forward, you can think that there are many application opportunities for autonomy on one of these kinds of machines. They put all kinds of attachments on these. They put augers on them and trenchers and excavators and grading things and stuff. We just happen to have picked the bucket as our first look.
Are the students limited to a single set of sensors, which are on the bot? Well, I'm calling it a bot because that's fundamentally what it is. Yeah, I have a...
Okay. All right. This comes up all the time. This comes up all the time at work. I ask somebody, I say, I'd like you to generate a stereo vision sensor. And they come back and they have an IMU and a whole bunch of other stuff added into the system, okay? So we can consider additional sensors, but in general, the answer is no. We want you to work off this point cloud, okay? Huh? Well, they won't. Okay. So there's a question. Joseph just said, well, there'll be IMUs on the bucket. Well, yes, there will be IMUs on the bucket. And with that, but you won't have them. What you will have is the pose or the position of the bucket relative to the machine, okay? So this points something out that we didn't do a very good job of covering, and that is this machine there's a whole ecosystem of functionality here. Some of it is specifically under your control, and some of it is there to service your needs. So for example, we will have a system that will be able to tell you where the bucket is in its range of travel. You'll need to know that in order to use the bucket effectively. We'll provide that to you. We have a vision-based navigation system that will drive this bot to a target pile. We designate in a viewfinder the target that we want to drive to, and this thing steers itself, and it'll chase a moving target, in fact, okay? That's not part of your scope, but it's part of the whole ecosystem of the machine, and that's why you don't have to find the pile. You just have to evaluate the pile, okay, because we'll get you there. So there's things like that. The communication systems in this, there's in the top side of this, engineers have been touching this, okay. We have the architecture of this top level is the interconnection, the communications, and the master control system for this. So internally this talks Ethernet, and externally it has Ethernet over Wi-Fi to a remote computer. That computer is running the ROS framework, and so the commands are generated by the various nodes and services in the ROS framework and transmitted here, where they're interpreted by this layer, and then transmitted from here to the machine control layer, which is below here. And we use an Arduino to control the motor drives for the implement and for the tracks. Okay? So this machine level is something that you should not need to get into. The intercom and master control level is something that you shouldn't need to get into. Your work will primarily be to generate a ROS node and or service that does the function of your algorithm. Okay? Since you will probably not be very happy with the vision system that we're providing to you, the stereo vision, you may want to make some improvements there, see if you can do a better job of processing the disparity map and get yourself a little bit better point cloud out of it. But the worse point cloud you can work with, the more stars you get. So, okay? Because remember, we're trying to work with small data. You know, we have ways, I can put a $70,000 LiDAR on top of the machine, and I can capture a 5 million point cloud of the pile, all right? I can do that. But to be able to take a couple of thousand points or a few hundred points off of this kind of crummy system that have large amounts of uncertainty and still be able to get the bucket filled because you're finding out just the parts that you need, just enough of what you need to know, that's truly clever, okay? So that's what we're trying to accomplish. And that has big implications in the commercial marketplace, because if we can do that with that kind of small data and those kinds of inexpensive sensors, then we can put autonomous machines in the hands of gardeners and small contractors and small farmers and construction people in second and third world nations and so on. So huge market, huge service to mankind if we can focus on this, you know. And the thing that's interesting in industry is it's kind of not glamorous, a little bit hard to do that. So what we find with most of the established vendors in this area is that They're putting really nice global shutter cameras on here. Pretty much the least expensive stereo head that you can buy is around $1,000. It's got a couple of gray point cameras in it. Yeah, it's really nice, right? It's really nice. It's high resolution. It's all those things. But it's a lot of money. It's a lot of money for a farmer in India or in Africa to be able to use to work around on his field. So we're trying to do this we're trying to capture this kind of other emphasis. Okay? That make sense? Service to mankind. Really cool. Question is, are there any safety issues? Okay. Well, here's our take on that. Yes, there absolutely are in any real application. The thing that I would say is that there are a lot of people in the world working on those things, and I think that problem is very well understood. The kind of techniques that are used for that are object recognition and hazard classification and so on and so forth. And there are whole companies dedicated to this particular study. We're going to relieve you of the distraction of that by saying that we'll have people guarding the workspace and cones set out so that we will not allow you to harm any of our executives during the demonstration. So you don't have to be distracted with those kinds of ancillary functions. But absolutely, if it were a real product, that stuff has to be integrated. Thank you very much for having us here. We're really excited to have the opportunity to do a project with you.
Hello?
Okay. Good morning, everybody. You're all wide awake? Yeah, right. I'm Homer, and as Tamara said, thanks for having me here. I run an organization called Clean Oceans International, and it's all about how do we get plastics out of the ocean, out of the marine environment. We're just about 10-year-old organization, and we started off, just a tiny bit of background. I'm a boat captain. That's what I've done for just about 40 years, and I've been really lucky to have that take me a lot of interesting places around the world, almost always by boat. And so I've seen a lot of ocean, and over that period of time, I've seen that the oceans are starting to have a pretty rough go of it. Overfishing is significant and very easy to see. Acidification is a little more difficult to see, but nonetheless equally insidious. And of course, then we get to plastic pollution. And plastic pollution is one of those things that you really don't have to have a whole lot of background to understand the impact. Almost anywhere you go at the beach, you're going to see plastic on the beach. And in some of the most incredible, wonderful, beautiful, pristine environments on the planet, they're not pristine anymore. They're absolutely just covered in plastic waste. And having seen that, I got inspired to see if there was something that perhaps I might be able to do.
I like talking. I just read a study today that in, what year is this? By 2040, I think there's going to be more plastic in the ocean than fish. I think that's really interesting, right?
So anyway, yeah, you look up the statistics and details and stuff, and they usually paint a pretty grim picture about what's going on now and what is likely to happen in the future if we don't do something different. And so that's what I decided to see if there was something different that I might be able to do. I got involved with a few folks from around town here, and we started a program called Clean Oceans Project. And at that point, the idea was, how do we get plastic out of the Pacific Gyre itself, go harvest it and recover the plastics from there and then do something with it. And in order to do that, I was kind of the engineering person on the team. I decided, okay, my job was to figure out how to actually achieve that. So I broke it down into 3 jobs: locating the amounts of plastic and trash that you'd need to justify the effort that it's going to take. And then how do we get it out of the environment without causing any further harm to the environment? And then third, but probably the most significant, is what do you do with it when you are successful in numbers 1 and 2? And the answer to that third question is kind of what led us down the road where we are today and the reason that I'm here this morning. Okay. So as you can read on the slide, and you've got access to this later if you'd like it, our mission is, part of our mission is accelerating the global adoption of PTF. PTF stands for plastic to fuel. We modified that nowadays. We call it PPTF, meaning portable plastic to fuel conversion. And it is the only method that I'm aware of in terms of recycling that at the end of the process, the plastic that you were recycling is actually gone. Otherwise, if you're recycling plastic, you're making a new plastic product out of old plastic. You still have a recycling challenge at the end of the life of that product. And almost always, you're only able to recycle a couple of different times, and the polymers themselves break down. And then you have a further recycling issue with spent polymers. So in order to do what we're planning to do, we want to show people that this technology works. And in order to do that, I'm going to go back. The goal of our present program is to deploy 100 plastic-to-fuel machines globally at the end of a 5-year project. And we're trying to begin that project right now. It says status on version number 1 of our machine. That's me leaning against the current high-end model that we have. We have 2 models with Clean Oceans International. One is about as large as these computer monitors here on the desk in front of me, and the other one is there in the photo that I'm leaning against, about as big as a dining room table. So that has allowed us, in conjunction with students here in the IDEAS program at UCSC, to prove that this actually works and begin the process of monitoring how much power is required to do the whole processing. At this point, that particular machine would not be considered economically viable, in that it wouldn't be able to process enough plastic to pay for itself and pay for anybody else to do that. But it's a step forward, and it's the initial step into actually addressing plastic waste management on very small scales. In this particular case, it's a manual plastic to fuel process, and then we want, in our program, that's what we're coming here with you guys, is to help us automate that process and then optimize that process by putting sensors on the devices that allow us to more closely control, understand what's happening, and control what's happening. Really simple diagram about what it is with our plastic to fuel conversion system. Up at the top there, you've got our plastic hopper. Take the product material, grind it or shred it or pelletize it into pieces small enough that it will then gravity feed down into that first horizontal tube. There's one of the two moving parts. There's a little feed screw there with the motor on the end, which begins pushing the product down the horizontal pipe. That begins the heating and melting process. Usually by the time it gets to the vertical stage, which we call the reactor, it's already fairly fluid, maybe a little bit more viscous like honey or something, and it pours down into the reactor. In the reactor chamber, there are heaters also that brings it up to about 800 degrees Fahrenheit, and at that point it is evaporated. It then goes into our third stage, or the evaporative fractionator, and there it's kept at specific temperatures, and so each element can then be distilled off, and the result that we're looking for is to create diesel fuel mostly, and generally speaking we get a little gasoline. If you want to, you can take that to a number of different levels, all the way down to propane and butane, and that's of course exactly what happens in the large refineries that you see, up in Richmond and that sort of thing. There is some sort of a residue left over, and that depends on how clean your feedstock was at the beginning. Very simple. Our system does 10 pounds of plastic an hour and creates approximately a gallon of fuel from that process. So what we're looking to do is try to, again, optimize that process for small-scale conversion use all over the planet. We'll use the instrument there in phase one as our test scenario, the machine that we want to do the modifications to. Right now, again, we just have the option of monitoring the energy, the electrical energy that goes in, but we would then want to monitor the heat, the rise in heat versus time, viscosity on the fluids at different stages in the process, and then the composition of the chemicals dependent on the feedstock. We have cooperation. One of our members works for Samsung, and Samsung's provided some electronic components that they would like to offer for use in this process that we're trying to do, with the object of being able to then transfer that information from the data sensor over the web, remote sensing, that sort of thing, so we can follow the progress anywhere. The particular system that we have employs a catalyst. We'd like to compare the use of that catalyst versus the lack of use of that catalyst. And then in the distillation process, we want to know exactly what our best endurance or residence time in the system versus temperature, how to optimize that. So basically, yeah, we want to find the most efficient process in terms of energy use. And of course, with efficiency comes a little bit of cleanliness. And the object of the game is to produce a system that has virtually no toxic output. For our design parameters, we've got a few things that we're working on, and we have not completed all of the parameters for the design process. Basically, we want them to fit into commercially available container systems, be they airport containers or shipping containers of 10 by 10 by 10, or perhaps a 10 by 10 by 20, and we're thinking that maybe we'll have 3 separate stages of the competition. Those parts of the rules have yet to be worked out. We wanted to employ simple components that you can then order through Amazon, if you will. You can get them almost anywhere. That's really important for many of our clients are going to be in very remote locations, and the opportunity to replace a heater or a motor or a chain or something like that has to be relatively simple. There are 2 styles that are called batch or continuous process, and the batch is basically like a big pressure cooker. You open the lid, put your materials inside, turn it on, let everything get to temperature and evaporate, turn it off, let it cool off, clean it out, and start over. The continuous feed is efficient in terms of its production capabilities, but you then also have to put the energy in of how to prepare your feedstock, be it grinding it or pelletizing it or something. And so the final judgment of this is how much energy is going to be required across the board, all the way from preparing or storing your materials, all the way through storing the liquid fuels that you contain. This product, the end product, has to be a commercial quality fuel product. That is, in the industry, we quite commonly refer to that as a drop-in fuel, meaning that I can take a bucket of this gasoline or diesel fuel, as we might create, pour it into my machinery, operate that machinery, and not void any manufacturer's warranties. I want the system, or we want the system, to run on electrical power for a number of reasons, and one of them is safety. And safety, 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 those are the 3 things that matter. We also want the opportunity to be able to use this onboard ship that will then be perhaps addressing plastic cleanup in remote locations. So electrical energy is really an important part for that. And of course, as I mentioned before, we want to eliminate toxic waste at the end of the process. Working with anybody and everybody around the planet that's interested in reducing plastic waste. Some organizations are a little bit proprietary in what they want to do. We're wide open. We're ready and willing and able to partner with anybody that has these same goals in mind. There are a number of manufacturers of plastic-to-fuel technology out there today. None of them at this point has a commercially viable system for, for this portable plastic-to-fuel systems, and that's what we're doing. We're trying to approach the low end of the production market. So where do we go from here? We want to, again, get our system up and running well enough so then we can come up with prototype monitoring systems that will, of course, log all of the data involved in production of plastic into fuel. As I said, heat rise calculations versus time versus power required, all that sort of thing.
So your job as a team would be to help them achieve that, right?
That's the object of the game, yeah. We want you to do this.
To sense, right, to outfit their device with sensors and communicate that data so they can come up with the viable specifications for a design competition.
Is that making sense? I thought so. Good. Yeah, so that's all, set up so that we can run this design competition, and at the end of it, we're able to compare the different versions of it, apples to apples, as they say. So we'll have very specific requirements, and we'll be able to judge those against each other. And we're planning on learning at every stage of this thing. We'll evaluate the plans on our way in, and of course we'll see what happens on the way out of the competition. And I'd like to see this kind of a competition be something that we happen and renew annually so that we just keep getting better and better at this. The objective, again, is to produce 3 or 4 top-level designs, deploy them out into the real world, test them against each other, and eventually have systems that really do make a difference in remote locations and small communities such as ours all over the planet. And of course, that's the bottom line for all of it, is we want to save our planet. I've got just a few minutes here. We're running a little bit behind schedule, but do any of you have questions about what we're doing or how you might want to be involved? The question is, what kind of plastics can we convert? This system here is optimized for what's are called resin codes 2, 4, 5, and 6. That is the low and high density polyethylene, which might be food service containers. The low density polyethylene is maybe your plastic bags that you get your groceries in, your Ziploc bags. If you're getting your fancy shirts done at the dry cleaners, that kind of plastic film. That's also the type of film that they put on the strawberry fields out in the agricultural zones, thin film polyethylene. The more rigid polyethylene might hold your Odwalla juices. Polystyrene and polypropylene are also made into food service containers. You might find polypropylene is that yellow rope that is so common down in the marine industries on the crab boats and such. Of course, styrene, most of us think of styrofoam. So those are the types of candidate plastic that are most easily digested by this system. Yes, sir. So the question is this a type of technology that we would put on a ship to go out into the ocean to try and clean it up at sea? And the answer is kind of yes and kind of no. Now, it is possible to put this technology on board a boat, and actually we have the boat that's in the photograph right here is currently in Spain, and it has our smallest machine, the one that I say is about as big as these two monitors together, and that is for show and tell, and it's certainly not for a commercial purpose, but it's there to demonstrate to smaller communities that this is a process that we can shrink down even to that level. So it is possible to do that, and it is possible to do cleanup. It is not commercially inviting to do that because the logistics and the costs of working at sea are pretty dramatic. However, our vision is that, let's say we have a small island community out in the middle of nowhere. Right now, their options for dealing with their plastic waste would be to burn it, bury it, or bag it up and throw it in the ocean for somebody else's problem. Or one other thing they could do is they could pay somebody else to come and pick it up, who would then burn it, bury it, or bag it up and throw it in the ocean. So right at the moment, the options that are available are not really very attractive. This, by bringing this plastic to fuel conversion system that's custom fit to that community's needs, they would then be able to process the plastic waste, not only that they generate, but perhaps what kind of might end up on their shore from a neighbor that doesn't have this system, until such time as that neighbor has that system as well. And so now they have created a fossil fuel, so it's not really the best thing yet for climate change, but that fuel is about a 14% reduction in its carbon footprint just in the way they make it. So that's a step in the right direction. You then eliminate the need to import that much fuel. That's a step in the right direction. You eliminate the need to export that much waste. Another step in the right direction. And in many of those instances where the processing that is done by just plain old putting it on the ground and lighting it on fire, well, you've reduced greenhouse gases dramatically because that's a horrible solution. And so you've kind of got a carbon reduction at every step of the way. Yes, sir. I'm sorry, I couldn't hear that very well. Okay, the question is about how much energy this requires to do this. Our initial look at it suggests that running all the extra peripheral machinery and such with the lights and everything, we might be using 20% or so of the energy that we produce. And so far, that seems to be a very attractive equation. That's part of the competition that we want, is to then find out if we can get even greater efficiency still. Sir. Okay, yeah, so the question is basically about sorting through and cleaning the plastics prior to processing. Now, every one of these systems is slightly different than another. As a general rule, they all, I find it very interesting that all of the manufacturers that I've had conversations with have given me basically the same information. It operates, again, 10 to 20% of the energy that you create is what you need to run the system. Those numbers seem to be fairly consistent. And also 10, 15% contaminant by weight. So let's just say that all of you brought your lunch in a brown paper bag and you had your peanut butter and jelly sandwich inside a plastic bag that's in there, and at the end of it we collected all the plastic bags. Well, there's a little bit of PB&J left on the inside of it. We toss it in the machine. As long as there's not more than 10 or 15% of that, that will then just be cooked at 800 degrees and become a carbon char, which is a candidate to put into your garden. I'm not sure if I'm quite ready to put that stuff in my garden yet, but that's what the manufacturers tell us, so let's decide if they're full of it or not. Anything else? Well, thank you very much for having us. We really appreciate it.